Hello, my name is Elena Onion. I'm with the New York State Department of Environmental Conservation, and I'm here today to present our work analyzing our long-term monitoring network. So we found that lakes in New York State's long-term monitoring network are browning, warming, and phosphorus limitation is declining. So lake monitoring at the New York State DEC is mandated by the Clean Water Act, Section 104, and Environmental Conservation Law, Article 17. Both require the state to maintain and operate a surveillance system, and that's the exact language they use, for the purpose of detecting changes in water quality for better or for worse. Like many mandated monitoring programs, the strategy employed in New York State's long-term monitoring network is to measure a consistent set of parameters and a consistent set of water bodies selected to represent statewide conditions. In this study, we examined our 35-year data record to understand the change and the drivers of change that were captured by our existing monitoring network and their implications for management of our environmental resources and future monitoring objectives. In the 35 years since the monitoring began, there have been many drivers of water quality change that this surveillance had the potential to capture. For example, Carpenter, Stanley, and Zayden in 2011 synthesized the drivers of water quality change into these 6 categories: climate change, hydrologic change, land use change, change in chemical inputs, aquatic invasive species, and harvesting, which is primarily fishing pressure. So our first prediction was that changing nutrient concentrations are driving changes in primary production. This nutrient paradigm is fundamental to lake management and was the driving idea behind our monitoring design at the beginning. Phosphorus specifically because there's ample evidence in the literature that phosphorus is a controlling parameter for algal biomass in temperate lake ecosystems. For this reason, phosphorus has been used for both water quality standards development and watershed planning efforts in New York State. Our second prediction was that the region-wide drivers of change, climate change and acid rain deposition, would also be apparent in our long-term data record. Climate change has impacted lake temperatures across the globe. Similarly, declines in acid rain deposition have led to lake browning in many regions of the world due to increased mobilization of organic matter. Even though our monitoring program wasn't designed to detect these changes, the impacts are broad-reaching and significant, so we expect to see them in our New York State data set as well. I need to give a shout out to the citizen scientist of New York State because the majority of the data collected in our long-term monitoring network were collected by the Citizen Science Lake Assessment Program. Our in-house lake monitoring network has mostly focused on specific research questions and screenings, so a big thank you. So jumping right into it, we found that epilimnetic waters are warming. Water temperatures have increased in the majority, so that's 77% of our lakes since the long-term monitoring program began in 1986. And this is according to a Kendall-Tao seasonal trend test. This map shows the range of temperature change we've seen statewide, mostly increasing, some more than others. The median of this change was 0.65 degrees Celsius per decade, which is comparable to what has been observed previously. Here is a review paper from O'Reilly et al. In 2015, and actually one of the authors on this paper was our plenary speaker here this week at NOMS. And for our colder and higher elevation climate, the mean change in surface water temperatures was 0.55 degrees Celsius per decade. And that's for lakes that are less than 21 meters, which 77% of our lakes were. So the trend in warming epilimnetic waters we are seeing across the globe, we're also seeing in New York State. As an aside, this is remarkable to me that we were able to detect this change since volunteers are using mercury thermometers that are difficult to read, in my opinion. So I really feel this is a testament to how dramatic an impact climate change is having on our lake ecosystems. Our second finding is that epilimnetic waters are browning. We use total color as a surrogate for colored dissolved organic carbon, and total color has increased in the majority, so that's 51% of our lakes in our long-term monitoring network. Here's a map showing the range of browning we are seeing across the state. Most sites are increasing. The median of the change is 0.0714 color units per year, which is hard to understand, but it's comparable to what's been published previously. Presented here is a review by Lapierre et al. In 2020 of Northeast regional brownification trends. So in other words, the regional brownification we're seeing in response to changes in acid rain deposition, we're also seeing here in New York State. The final trend that I'm reporting on today is that phosphorus is driving primary production. The majority of the lakes had statistically significant correlations between chlorophyll A and phosphorus concentrations. And this is according to a Kendall-Tau seasonal trend test of paired parameters. So presumably that means that phosphorus is driving those changing concentrations, but we dug into this a little deeper. We found that the phosphorus and chlorophyll relationship has changed over time. On the left is a graph plotting all of our phosphorus and chlorophyll data, and the line is a log linear model that best fits that data. On the right is a plot of the residuals, and just to be clear, residuals are a measure of the distance of each point from that line. So on the right, we have plotted these residuals against sample date, and as you can see, there are more negative residuals than at the start of the monitoring program, and this change has been very steady over time. So these residuals has declined very steadily over time. It's very striking to me. So this indicates that each unit of phosphorus today results in a smaller concentration of chlorophyll A compared to the start of the monitoring program. In other words, phosphorus limitation has declined steadily over the course of our 35-year monitoring record. To drive this point home, I made a simplistic animation to show how phosphorus limitation has changed. But a real-world example is that New York State's phosphorus water quality standard is 20 micrograms per liter. This amount of phosphorus is correlated with less chlorophyll today than in 1986. To be specific, it's 1.45 milligrams per liter less chlorophyll A, and that's close to a 20% change. So this is a pretty significant change that we're seeing. If you look at this change statewide, you can see the vast majority of sites have declining phosphorus limitation, some lakes more significant declines than others. We feel that acid deposition, specifically wet nitrogen deposition, may be driving the declining phosphorus limitation. So declines in acid deposition due to emissions legislation has decreased nitrogen inputs into our lakes, affecting the N to P ratio. With less available nitrogen, the power of phosphorus as a limiting nutrient has declined. In support of this, we observed more negative residuals from the log linear chlorophyll phosphorus model with decreasing wet nitrogen deposition, and that's the plot on the right. And this mirrors the decline seen with sample date, which is in the plot on the left, and I repeated that plot from the previous slide. We also observed declining N to P ratios in most of our water bodies. It was a slim majority, 51%, and this is according, again, to a Kendall-Tau seasonal trend test. Therefore, because of these two reasons, the declining residuals in the phosphorus chlorophyll model with wet nitrogen deposition and the declining N to P ratios seen here, we felt decreasing acid deposition and its direct impacts to lake N to P ratios is likely driving the steady decline in phosphorus limitation seen in our long-term monitoring network. Others have observed the opposite trend. As acid deposition increased in the 70s and 80s, they observed increasing phosphorus limitation. So as an example of this research, here is a plot shown from Hessen et al. 2013, and you can see that phosphorus limitation was shown to be higher at higher levels of nitrogen deposition. And in fact, one other author posited that acid rain deposition likely had an impact on Schindler's whole lake nutrient enrichment experiments, which is one of the most cited evidences for phosphorus limitation. It cannot be ruled out, she wrote, that the nitrogen deposition in the experimental lakes area in the early 1970s was high enough to relieve the lakes from clear nitrogen limitation. But I digress. My point is that this opposite trend has been observed by several others. Acid rain deposition increased in the 1970s and 80s, and we saw increasing phosphorus limitation. We are positing that our data is showing the mirror of this. Now that acid rain is decreasing, we're seeing a decline in phosphorus limitation. I have not seen this in the literature, and I'm hoping that someone in the NOMS community has and will let us know. Other potential drivers of this change in phosphorus limitation that we looked at were temperature changes and brownification. Temperature increases due to climate change have impacted phytoplankton composition and growth rates, and so could potentially be drivers of the phosphorus limitation change. And we did see decreasing residuals in the log linear phosphorus chlorophyll A model with increasing temperatures. That being said, that could also be a consequence of the fact that temperatures are steadily increasing over time, so it could just be a correlation and not a driver. Brownification could also be a driving cause. In high color lakes, we expect brownification to impact light limitation and thus reduce phosphorus limitation. In low color lakes, we expect brownification to increase phosphorus availability and therefore decrease phosphorus limitation. But we actually saw the opposite trends in our data set, so we don't feel this is a major driver of phosphorus limitation. In addition, zooplankton grazing, macrophyte growth, invasive species, and local catchment characteristics could potentially be drivers of this change, but we didn't have data sets to examine these impacts. We feel our findings have implications for management. So rising temperatures are correlated with harmful algal blooms, will likely impact internal loading and methane emissions, and have negative impacts on cold water fisheries. Brownification potentially will cause light limitations, impact oxygen concentrations, increase heavy metal mobilization, and can result in disinfection byproducts. Declining phosphorus limitation has the potential to impact our water quality standards development and watershed planning efforts because these are developed based on a presumed static phosphorus chlorophyll relationship. We feel this work demonstrates that these thresholds should be examined and revised on a regular basis to account for the fact that this relationship is changing steadily over time. We also feel our findings have implications for the design of our future monitoring program. It's true that there are drivers of change our monitoring did not detect. Some of these we could not have foreseen, which is really the benefit of a mandated monitoring program, with a surveillance system looking out for unexpected change. But there are some changes that we do expect, and we can do a better job designing our program to capture a broader range of change and drivers of change. To do so, we are going to continue our annual monitoring and our long-term trend sites, but we're also going to add random probabilistic sample design, which is the design employed by the National Lakes Assessment. And the reason we're adding this is because we recognize that this small subset of lakes is not truly representative of statewide conditions. We're hoping to bring in a broader diversity of lake size as well as watershed uses. We're also adding question-driven monitoring. We are participating in the Regional Monitoring Network, which is looking at the impact of climate change on our reference water bodies, and we're conducting a CEC study where we're examining the relative impacts of different land use practices on the occurrence of contaminants of emerging concern. So with that, I want to say thank you. This has been a valuable experience to take a retrospective moment and see what we've been able to capture and to help us understand how we should design our monitoring better moving forward. And this photo is of my lab notebook. I used it to explain my notes to my colleague, and then I left it on my kitchen table, and my daughter decorated it with all her wonderful doodles. It just goes to show that our children are watching us. And here's hoping we can push the needle and make a difference. Thank you.